In this lesson, we'll continue our investigation into spontaneous generation with the work of Louis Pasteur. Pasteur lived in the mid-1800s and was using the best microscopes of his age. Pasteur was aware of the existence of bacteria and also the controversy surrounding bacteria. Many in his time believed that bacteria could spontaneously generate from broth. Pasteur was also aware of the history of experiments on spontaneous generation, so he knew that Spallanzani's melted flasks posed a problem, because the believer in spontaneous generation could say that the boiling process would destroy the vital force in the air, which was responsible for spontaneous generation. And furthermore, because the flask was melted shut, no new vital force could get in, and this is why no bacteria were found in these vessels. Now, a key insight that Pasteur had about this situation was that he argued that bacteria might be able to travel through the air. Bacteria were found all over the surfaces of things, but he argued that bacteria could also travel through the air. How would they do that? They might be hitching a ride on tiny, tiny little dust particles. And if that's the case, then, from Pasteur's point of view, it's not that air has a vital force. Rather, air has dust particles in it which carry bacteria. So if air is allowed to mix with the broth, it's the bacteria on the dust particles that then enter the broth and then grow and reproduce, and you get more and more bacteria. So the key experimental innovation comes when Pasteur is going to design a flask that allows air into the vessel but blocks dust that might be carrying bacteria. The kind of flask he had in mind is shown here. Notice we have the top of the flask here, and it's not melted shut. Rather, Pasteur is going to use a flame to bend out the neck into a tube open to the air here, but notice that important curve right here. Pasteur will argue that that curve is sufficient to trap dust particles that might be carrying bacteria. And so you can block bacteria from getting to the broth while still allowing air itself to enter the vessel. When he sets up flasks like this and boils them for an hour, a few days later he finds no bacteria. Now, how does he determine that there's no bacteria here? Here's another key innovation. He's going to use not meat broth, but he's going to use sort of a broth substitute. And the key thing about that substitute is that it's clear. And that's important because when bacteria get into the clear broth, they turn it cloudy. They make it kind of dark. So all you would have to do is look for any cloudiness in the broth, and then you can infer that bacteria are growing. This meant that he didn't have to do Needham's checking with a microscope. He didn't have to take samples from the broth and check under the microscope, because that sampling process itself might introduce bacteria. So this was a nice innovation, that he didn't have to break open his vessels. If the fluid stayed clear, as it did in this picture here, he knew that there was no bacteria growing in that flask. So in addition to having flasks that had the curved neck, Pasteur also set up flasks that had a straight neck, but simply just broken off here, so they would be exposed to the air. Now remember, these kinds of flasks are situated in his laboratory where there's dust in the air. So we can imagine dust particles entering the curved part here, getting trapped so bacteria can't get to the broth. But for the straight neck flasks, bacteria will be able to drift down, hitching a ride on dust particles, drift down right into the broth, and bacteria will grow. And sure enough, for these straight neck flasks, when you boil them for an hour, wait a few days, they have bacteria. The broth is no longer clear. It now shows evidence of bacterial growth. It is cloudy and colored. In fact, if you go to Paris, France, and go to the Pasteur Institute, you can see some of Pasteur's original flasks. He made these flasks over 150 years ago. This one here, notice it has the curved neck here, open to the air. It still has the clear broth, indicating that no bacteria has entered in over 150 years. This flask was a straight neck flask, and it does show signs of bacterial growth. The clear broth has turned brown. Pasteur wanted to confirm that, in fact, his curved neck was trapping dust with bacteria, and he did something very clever. He took some of his flasks and he would tilt them so that the fluid, initially clear fluid, could wash down into the neck, and then he would tilt it upright again so the fluid would wash back into the vessel. This flask was tipped in that way, and sure enough, a few days later, the clear broth turned brown. Bacteria growth was evident here. This flask was not tipped, and so whatever bacteria was trapped in the tube out here never had a chance to get into the broth. Pasteur also did a number of other experiments where he would take a whole bunch of flasks and put them around in different locations around Paris and outside of Paris. So, for example, in his laboratory, he opened up or he fashioned these 3 straight neck flasks, so they're open to the air, and he would allow them to sit in the air for a time. And after a few days, all 3 of them here show evidence of bacterial growth. In fact, out of 11 such flasks, all 11 were contaminated. But this is in contrast to a set of flasks that he took high up on a mountain. So he went 2,000 meters high up a mountain. He carried 20 flasks with him, opened those up, so these are the straight neck flasks exposed to the air, and only one of them, 1 out of 20, was contaminated. And this indicated to Pasteur that the amount of bacteria in the air differs depending on where you are. In the city of Paris, there was more dust-carrying bacteria in the air than if you go to high elevations up on a mountain. Pasteur took his flasks to several other places. Out of 20 flasks at this location, he found that 5 of them became contaminated. Now, for Pasteur, how would he explain why 5 became contaminated and 15 didn't? Well, it had to do with the overall level of bacteria in the air that was floating around up there. But another part of the answer is just sort of chance. By chance, these 5 happen to have some bacteria drift down into the flask, whereas the other 15 did not. If there's just more bacteria in the air, then you'll get a higher percentage of your flasks contaminated. And so in Paris, 11 were contaminated. At this location, 5 of 20 were contaminated, and high up, 2,000 meters high on a mountain, only 1 of 20 was contaminated. In the end, then, Pasteur concluded that spontaneous generation is not happening with respect to bacteria. Bacteria come from other bacteria, in this case, bacteria in the air. No longer could a believer in spontaneous generation say that the failure of growth here, bacterial growth, is because the vital force couldn't get to the broth. The flasks were open. The boiling procedure, no longer could the believer say the boiling procedure destroyed the vital force, because after all, new vital force should be able to get into the flask. So Pasteur began to persuade others that in fact bacteria can travel through the air. And this is the final understanding that we've come to in the investigations of spontaneous generation. Spontaneous generation doesn't seem to be happening in nature today. Rather, living things come from other living things. The one exception, of course, is the modern understanding of the origin of life, where many biologists argue chemistry produced the first living cells. So that would be a case of spontaneous generation, non-living molecules creating the first living things. But since that time, Pasteur's work and later biologists have demonstrated that spontaneous generation does not happen in nature. Rather, living things come from other living things. Pasteur is entombed in a crypt in the Pasteur Institute, and on the ceiling he had the 3 Christian virtues painted: faith, hope, and charity. But he added a 4th, science. Pasteur was a passionate believer in the power of science to do good things for humanity.